Hello everyone, welcome to my videos. This is the second video for chapter 1 for the topic Fundamental Differential Equations. Hello everyone, welcome to my videos. This is the second video for chapter 1 for the topic of Fundamental Differential Equations. Let's get started. In this video, we'll explore the topic of directional fields. In particular, directional fields are useful to analyze the solution behavior for first-order equations, which can be written in this form: y prime equals a function f depending on t and y. So here, y is a function of t. Then in the yt plane, with t as the usual x-axis and y is the function value axis, then the derivative y prime can be interpreted as the slope of the tangent to the solution yt at that point of t and y. Let's discuss a few cases for the property of the slope for different values of y prime. The first case, if y prime equals 1, this means the tangent line at that point is horizontal. If now y prime shall be bigger than 0, then y is an increasing function of t at that point, and therefore the tangent line will go up and the instantaneous slope is positive. Finally, if y prime is less than 0, then the tangent line goes down and the slope is negative. Once we have determined the direction of this tangent line, then the absolute value of this y prime will tell you how steep the tangent line should go. The bigger the value, the steeper the tangent line will be. Now, with these informations in our hands, we can now analyze the solution for this equation in the yt plane and discuss qualitative behaviors of the solution. Let's take some examples. Consider this equation: y prime equals a half times 3 minus y. So here y is a function of t, and the right-hand side is a function depending only on y but not on t. And such equations, we will see through our solution strategy that they are easier to analyze by using directional fields. Okay, now let's follow the previous discussion and analyze the three situations. So first, when will y prime be 0? We see that when y equals 3, y prime is 0. So wherever in the yt plane y equals 3, the directional field will have flat slope. If now y is bigger than 3, then we know 3 minus y is less than 0. So y prime is less than 0, and the directional slope will point down. And finally, when y is less than 3, then 3 minus y is positive, so y prime is positive, and then we will have upslope. Okay, now let's look into details of how they really look like. Here is a graph with a lot of information, so let's be patient and look at them one at a time. So pretend it's a blank page, and now we focus on the case when y equals 3. So in the yt plane, y equals 3 will be a horizontal line. Along this line, the slope shall be flat. So we will draw little arrows pointing in the direction of how the solution y will change in t. So we'll have all horizontal little arrows here along this line. Okay, now let's consider the case y bigger than 3, so which will be the upper half of the line y equals 3, so up here. So consider the case y equals 4. And then here we'll have a downward slope, a little bit downward. All of these will have the same slope. Okay, so we will draw these slope, let's say a little bit all through. And now if you go a bit further up, say y equals 5, we know we will still have downward slope. And then because 5 minus 3 is bigger, then the slope will be steeper. So it will come down steeper with a negative slope, but they'll all be the same along this line. So all these little arrows are parallel to each other, but now they are steeper than these bunch of arrows. Okay, now consider the case y less than 3. Take, for example, y equals 2. Then we know from the discussion all the arrows will point upward, will have positive slope, and they're all the same here for y equal 2 along this horizontal line. And they are not very big. So I am talking qualitative here. Okay, and then for the smaller value of y equals 1, well, that will give us also positive slope, and then y prime will be bigger, and then therefore it will be steeper. So along this horizontal line we all have the same slope, but will be steeper going up. Okay, so let's take one more line, y equals 0. Again, it will all point upwards, the slope, and then also the slope will be even steeper than this previous bunch. Okay, so now we have completed the sketching of the directional field, the blue part in this graph. With this information available, we are now ready to discuss behavior of the solution qualitatively. So the first interesting point is along this horizontal line y equals 3. So we see that if the initial value y at 0 shall be 3, the direction line tells us that y would move horizontally. And then as long as y moves horizontally, and the solution remains 3, so it remains moving horizontally. So it will go on the horizontal line y equal to 3 following the arrows all the way until t goes to infinity. Now let's look at the case where the initial value of y is bigger than 3. Take, for example, y0 equals 5. How would the solution behave? We'll follow the directional field. Right here, it will come down with a tangent equal to these directions. So as it comes down, we know from the discussion, as this gets closer to 3, the tangent, the slope gets less and less. It's going down, but with not as steep, less and less slope. So it will slowly bend into a slower slope, and then here it will take the slope of y equal 4 as we sketched here, and as it keeps going it will get slower and slower slope, and eventually approaches y equal to 3 as time goes to infinity. And you can argue that this kind of a behavior is not only available for y equals 5, It would be the same also for y equals 4. Here you would come down, and then you would get flatter and flatter, and then asymptotically approach y equals 3 without crossing it. Okay, so you can conclude that from this discussion, if y0 is bigger than 3, and then as t grows, the solution becomes smaller and smaller, and then asymptotically approach 3. Okay, now let's discuss the case that y0 is less than 3. We can pick a point, because from the discussion up here, we are expecting they behave or similar. Okay, so pick the case y0 equals 1. And then from the directional field, we see the solution will go up. And then as it approaches 3, the slope will become less and less. So it will bend gradually. And then it will keep bending, and then it will never be able to cross y equals 3, because they're all positive slope here and get infinitesimally smaller and smaller, and as time t goes to infinity, this will just approach 3. Okay, and all solutions with the initial value less than 3 will all behave in a similar way. Say, if it's 0, then you will come up, and then you will bend and bend, and then you will gradually asymptotically approach 3. Okay, so summarize. I would like to stress this point. When y0 equals 3, then y equals 3, the constant solution, is a solution. We stress on that because this is a very interesting solution, and later we'll come back to it. And then the second observation is this asymptotic behavior. That is the behavior of the solution when t goes to plus infinity. We can also discuss when t goes to negative infinity, but we will not do it for this example. And we see from our discussion, no matter your initial solution, a condition shall be, let it be 3, or bigger than 3, or less than 3, all of them will asymptotically approach the value y equals 3. Okay, so you might be thinking now that this example, I picked the number 3. It's just a number. This behavior is more general. Okay, so let's look at that. Okay, so let's look at it in a slightly more abstract setting. We now consider the equation y prime of t equals a times b minus y, with a bigger than 0. This is important. Okay, so we claim that it will have similar behavior to the previous example, where we have b equals 3 and a equal half, and this is a positive a. Okay. Let's try to sketch the directional fields and look at properties of the solution qualitatively. Okay, so here I draw the axis y and t, and I marked the place where y equals b. So from our discussion, we know when y equals b, y prime is 0, so all the arrows here will be pointing horizontally. So let me just draw a couple of them. And then when y is bigger than b, and then the slope will all point downwards. Let's just pick a horizontal place and then sketch it. So it comes down and it comes down, approximately the same slope. It's a bit hard to draw with the pencil, Apple Pencil, so precisely. Sorry for the rough sketch. Okay, so when y is less than b, y prime, is positive, so it goes up. So let's draw a couple upward slope, which is a bit easier to make. Or these are parallel with the same slope. Okay, and okay, so how does the solution behave? We can try to draw red curves for the solution, and then we see that if the initial value shall be at y equal b, then this horizontal line is the solution. Okay, and then if y initially is bigger than b, what will happen to the solution? Well, it will come down, and the slope it comes down will gradually become less and less steep, and asymptotically it approaches b. And similar thing happens here, and if y is less than b initially, and then it will point upwards and gradually approach y equals b asymptotically. Okay, so with this rough sketch, just a few arrows and a few lines, and we can conclude that for this type of equation, no matter what values of a and b we have, as long as a is positive, then solutions with any initial value will asymptotically approach y equals b as time goes to positive infinity. Okay, so in this discussion here of the solution, you would be thinking that it makes sense to assume a is bigger than 0. Because if a shall change sign, then the y primes will change sign. Then the solution will behave in a very different way. Okay, so this is the very first example of directional fields. So it's the simplest possible case, and later on we'll look at more complicated cases. Okay, so let's look at this case with some details. Let's consider the same equation in this same general setting, except now a is less than 0. Then the sign of y prime is all changed, and let's quickly sketch it. Okay, so let me draw 3 parallel lines horizontal, where the middle one is y equals b, and the top one is y bigger than b, and the lower one is y less than b. So from our discussion, we can quickly put the arrows. So when y is b, it will still go horizontally because y prime is 0. Okay, and if now y is bigger than b, then we actually will have now y prime bigger than 0. So, and the arrows will point upwards. Let's draw just a couple. And then when y is less than b, I have the arrows actually go downward. Okay, I'll just make 3 of them. Right. So now how do you sketch your solutions? Let's look at the first case. Y equals b is interesting because if you, as long as you stay on y equals b, really stay on, then you remain on the y equal b. You will not divert because it says you go horizontally, right? So you can say that if y0 equals b, then y equals b is a solution, the constant solution. Okay, so second, now if y is initially a little bit bigger than b, come up here, what will happen to the solution? Well, if you are bigger than b, then the slope is positive, so you will start going up. And then as you go up, and the slope gets bigger and bigger, and then you go up faster and faster. And as t goes to plus infinity, you go to plus infinity. Okay, so that's what we concluded here. If y at 0 is bigger than b, then y goes to plus infinity, asymptotically. Okay, and the final case is when y is less than b. Then you know the y prime is less than 0, so you will start to go down. And then as you go down steeper and steeper, and then you bend more and more and more downward. So you know as time goes to plus infinity, the solution will go to negative infinity, which is stated here. Okay, so one interesting observation one can say is that the constant solution here, although it is a solution, we call this a unstable solution, because if you are just a teeny bit drifted off with some perturbation, unfortunately you drifted a bit down, and then you will drift away from that and go to negative infinity. And if you shall drift a teeny bit up, and then you will start to bend further up and go to plus infinity. Okay? So this is the very first example for directional fields. So it's the simplest possible situation. In later videos, we will cover some more complicated ones. Okay, so let's end the video on a lighter note. So here's a question. Why should you never argue with an angle of 90 degrees? The answer? Well, because they are always right. Okay, so I hope you enjoyed this video, and I'll see you next time.